Okay, imagine for a second you found another you out there in the cosmos. Someone incredibly similar, maybe they share your exact DNA, your life experiences up to a point, but then they made just one different choice. What could you learn?
Wow, that's that's a profound idea, isn't it?
Yeah.
That kind of mirror self could reveal so much about, well, how small differences ripple
Or
outward.
maybe highlight things about your own path you'd never really considered.
Exactly.
Right. Well, astronomers are doing something, well, pretty similar, but, on a cosmic scale. This deep dive is all about solar analogues.
Stars out there in the galaxy that are, or maybe were, or perhaps will be, remarkably like our own sun.
Yeah, and we're pulling insights for this deep dive from some seriously powerful sources. We're leaning heavily on the incredible data from the European Space Agency's Gaia mission.
Especially the analyses using the Gaia DR3 data release. That's key here.
Our mission today is to really unpack what makes a star a solar analog, why scientists are putting so much effort into finding them, scattered across the galaxy.
And what these cosmic doppelgangers can teach us,
Yeah.
sometimes in ways that are, well, surprisingly fundamental.
Even about our own sun, right?
Absolutely.
Right.
So let's unpack this. When we talk about a solar analog, the term itself is often used, well, quite broadly.
Okay.
It generally means any star that looks very similar to the sun in its main characteristics. Or like you said, one that might have been similar in the past or will be in the future as it evolves.
But the sources dig deeper, right? They mention more specific categories like solar twins. That sounds like a much closer match.
That's right. Yeah, solar twin is a much stricter definition, a subset of analogs.
That's true.
We're talking stars considered essentially identical to the sun across, well, pretty much all the key astrophysical parameters.
Like what?
Mass, age, luminosity, its detailed chemical makeup, temperature, surface gravity, magnetic activity, you name it. The works.
So basically a near perfect cosmic replica,
Exactly. And the sources really highlight that these solar twins, they're seen as the most promising places to look for planetary systems like ours.
meaning potentially Earth-like planets.
That's the hope. Planets potentially suitable for, you know, carbon-based life with liquid water oceans.
Mm.
Prime targets.
Okay, so analogs are broadly similar. Twins are almost exact copies. Got it. What about solar siblings then? That sounds different. Like family?
Is a different concept, yeah.
Mm-hmm.
Not about being identical now. Solar siblings are stars that scientists hypothesize formed with our sun.
From the same initial cloud of gas and dust.
Exactly, from the same huge stellar nursery. So they wouldn't necessarily have the same mass or temperature today, but they would share the exact same age.
Oh, yeah.
The same original chemical recipe as the sun when it was born, and crucially, consistent galactic kinematics, meaning they'd have started out moving together through the galaxy.
Like litter mates, but for stars.
Kind of, and finding them is an active area of research. The sources mentioned using Gaia DR2's movement data.
The earlier data release.
Right.
Yeah.
A study back in 2018 identified a top candidate. They nicknamed it Solar Sibling 1. It's quite far off, maybe 360 parsecs away, give or take 80.
Wow. And has the newer Gaia data, DR3, found more?
Well, according to the sources we looked at, Gaia DR3 hasn't really solidified any more convincing sibling candidates just yet.
Huh.
Yeah, including some stars that were suggested before Gaia's precise data came along, like HD 186302 or HD 162836. So the idea is compelling, but actually verifying these siblings is proving pretty tricky.
Okay, so we've got the different types down. But why? Why are scientists so keen on hunting for these sun-like stars? What's the big scientific payoff?
That's a really important question. Fundamentally, the goal is that solar analogs give us unique perspectives on our own sun.
How so?
Well, they let us see what the sun might have looked like at different points in its life. Imagine observing our sun when it was only, say, a billion years old.
Or seeing what it might become billions of years from now, like a cosmic time machine.
Exactly. It's like having snapshots of its past and future. And that perspective opens up a surprisingly wide range of scientific applications.
Okay, like,
For instance, by studying the really tiny chemical differences between the sun and stars that are otherwise very similar.
the analogs and twins.
Right. Researchers can ask a fundamental question. Is our sun typical? Is it chemically average compared to other stars that might host Earth-like planets?
Or is it maybe a bit special, an outlier?
That's the nub of it. And the sources point out something really interesting here. When you compare the sun's composition to nearby analogs matched for iron content,
Okay.
our sun is actually quite rich in volatile elements. The ones that turn into gas easily.
Richer than most similar stars.
Yeah, it seems to fall into the top 10, maybe 15% for that characteristic among nearby analogs.
Wow. Why would that be?
Well, one intriguing idea mentioned is that this pattern, this abundance, relative to how easily elements condense, might actually be linked to planet formation itself.
Wait, linked how?
It could suggest that the process of forming our planets selectively gathered more gas versus dust compared to other systems, subtly changing the sun's final surface chemistry.
So our planets might have tweaked the sun's composition. Whoa, okay, that's a mind blower. What else can these analogs tell us?
They're incredibly useful for stellar age estimation. This is a big one.
How do they help with that?
They help scientists find and calibrate specific chemical signatures in a star's light, its spectrum, that change predictably over billions of years. They act like spectroscopic clocks.
Clocks based on elements.
Exactly. The sources specifically mentioned the ratio of yttrium to magnesium, YMG, as being a particularly good age indicator for sun-like stars.
Clever. So chemical clocks, what else?
Moving closer to home, they're surprisingly useful for studying things in our own solar system.
Like what? Planets.
Even smaller things, like asteroids.
How does a distant star help study an asteroid?
Well, our sun's light completely overwhelms the faint light reflected off an asteroid. But if you find a solar analog, a near-perfect match to the sun's light...
Ah, you can use its spectrum as a template.
Precisely. You subtract the analog spectrum from the asteroid observation. This removes the sun's glare very accurately, letting astronomers see the asteroid's own subtle spectral features much more clearly.
Which helps figure out what minerals are on its surface.
Exactly. It aids in mineral classification. It's a really neat trick.
That is clever. Using a distant star to study local rocks, the applications seem really broad.
They keep going. Analogs are absolutely crucial for really fundamental astronomical work, like setting the 0 point for photometric calibrations.
Making sure brightness measurements are accurate and consistent everywhere.
Yes. That's how we ensure that when we measure a star's brightness through different color filters, those measurements mean the same thing, whether the star is here or across the galaxy. It underpins so much.
Calibration is king in astronomy, right?
It really is. And they're also used to test our computer models of stars, how schemes work inside. Through astroseismology, studying the tiny vibrations, the star quakes, on a star's surface. Those vibrations are like echoes, telling us about the star's internal structure. Solar analogs provide key test cases for those models.
Listening to a star's heartbeat, almost.
A good way to put it. Plus, they contribute to understanding how the chemical composition of our whole galactic disk has changed over billions of years.
Mapping cosmic chemical history.
In a sense, yeah. Each analog is a data point. And they even offer insights into nuclear astrophysics, how elements are made inside stars and in supernovae. Things like neutron capture elements or patterns seen in supernova debris.
So they connect to pretty much everything in astrophysics.
They're real cosmic multi-tools. But maybe the most surprising application, the one you might not expect, is in fundamental physics.
Fundamental physics, how?
There's a project called the Survey for Distant Solar Twins, or SDST. They're using solar analogs to search for tiny variations in something called the fine structure constant.
Wait, the fine structure constant. That's like the number that governs the strength of electromagnetism, isn't it? A fundamental constant of nature.
That's the one, alpha. The SDST project looks at very specific patterns of absorption lines in the light from these distant sun-like stars.
Okay.
And measures them incredibly precisely to see if those patterns shift at all. A shift could mean the fine structure constant isn't perfectly constant everywhere in the galaxy.
Wow. So they're using stars like our sun to test if the basic laws of physics are truly universal. That's a huge deal.
It absolutely is.
Yeah.
And the sources mention their latest results, looking at analogs up to 4 kiloparsecs away.
Yeah.
Quite distant.
Did they find anything?
So far, they haven't found any evidence for large variations, at least locally within their sample. They put really tight limits on how much it could possibly vary, less than 50 parts per billion.
Still, the fact they can even test that is incredible. Okay, so solar analogs. Perspective on the sun's life. Cosmic clocks, calibration tools, asteroid science, galaxy evolution, testing fundamental physics. Amazing. How does Gaia fit into actually finding all these useful stars?
This is where Gaia has been completely revolutionary. It's a game changer.
Why Gaia specifically?
Because Gaia performs spectrophotometry measuring colors and basic spectra for billions of stars,
Yeah.
all in a uniform way. This creates a massive, consistent data set perfect for systematic searches.
A uniform survey.
Exactly.
Yeah.
And crucially, Gaia measures parallax with unprecedented accuracy. That gives us precise distances
What you need for...
for figuring out a star's true luminosity, its radius, its mass, the fundamental properties you need to check if it's really like the sun. Distance is key.
So Gaia provides the huge, accurate data set needed to sift through the galaxy and find these needles in a haystack.
Precisely. And researchers are really diving into this data. There was a study led by Yana Galarza and colleagues in 2021.
What did they do?
They used Gaia DR2 and EDR3 photometry brightness and color data, combined with spectroscopy from ground-based telescopes, focusing on stars relatively close by, within about 100 parsecs.
And how many analogues and twins did they find in our local neighborhood?
Using their specific criteria, they reported finding 46 solar analogues and 9 solar twins.
Okay, 46 and 9 nearby, but you said Gaia was revolutionary.
Right, because that was just the start. A much bigger study by Creevy and colleagues in 2022, using the full Gaia DR3 data release, really scaled things up.
How did their approach differ?
They started by selecting stars based on brightness, but critically, they demanded really high-quality parallax measurements, less than 5% uncertainty.
Why that specific cut?
To make sure they could reliably place the stars on the Hertzsprung-Russell diagram, the fundamental plot of stellar temperature versus luminosity, and also ensure the stars were bright enough for detailed follow-up studies later. A smart filter.
Makes sense. What else?
They then used results from Gaia's own internal data processing pipelines, tools like GSP-Spec, which analyzes Gaia's spectra, and FLAME, which estimates stellar parameters.
So they leveraged Gaia's built-in analysis?
Yes, they looked for stars with estimated masses between about 0.95 and 1.05 times the sun's mass, and radii between 0.8 and 1.2 solar radii. And they also checked for chemical abundances consistent with the sun.
A very systematic, multi-pronged approach using Gaia's power. And the result, how many candidates did they find?
Get this. Their rigorous process, using the spectral analysis, yielded a list of 5,863 high-confidence solar analog candidates.
Wow, from 46 to nearly 6,000.
Exactly. And using a separate, slightly less strict method based just on Gaia's colors and spectra GSP-5, they identified a potential list of, wait for it, 234,779 solar analog candidates.
Whoa, hundreds of thousands. That's a whole different ballgame.
It completely changes the landscape for this kind of science. It's a massive increase.
And didn't you mention the SDST survey also uses Gaia?
Yes, the one searching for fine structure, constant variations. They use Gaia EDR3 data too, specifically to verify their spectroscopic estimates and pinpoint the locations of their target analogs and twins, which they're searching for, out to much greater distances, like 4 kiloparsecs. Shows Gaia's reach.
Okay, you teased something earlier, a surprising fact about the sun's color. How on earth does finding distant lookalikes help us measure the color of our own star right here?
Right, it sounds weird, doesn't it? But here's the thing. Even though the sun is right here, super bright, it's actually surprisingly difficult to measure its color accurately.
Difficult. It's the brightest thing in the sky.
Exactly. It's too bright. It completely saturates the detectors on telescopes designed to measure faint, distant stars.
Ah, okay.
You can't just point a regular telescope at the sun and measure its color in the standard astronomical filter systems, like the UBVRI or even Gaia's own GGBP, GRP filters. You need special equipment, and translating those measurements into the exact same standard system used for all other stars is really tricky.
I see the problem. So how do astronomers get around that? How do they figure out the sun's standard colors?
Well, one of the best ways, and this has been used for years as the sources note, is to find these solar analogs and twins, stars that are as identical to the sun as possible. And then you measure their colors using standard telescopes and filters because they are faint enough. You average the colors of the best matches.
And infer that that must be the sun's true color in those standard systems.
Exactly. It's like using a perfect stand-in when the original is too bright for the stage lights. A brilliant workaround.
Okay, that makes sense. And the recent Gaia studies helped with this.
Immensely. That Creevy et al. Study from 2022, with its huge sample from Gaia DR3, made a big leap here. They took their list of 5,863 analog candidates.
Yes.
And they carefully selected a super clean subset, 682 stars that had almost zero interstellar reddening, meaning hardly any dust between us and them messing with their color.
I got it. A clear line of sight.
Right. And with that pristine sample of sun-like stars, they could calculate really precise average colors for the sun in the Gaia passbands, and also some infrared ones.
How precise we're talking.
Really precise. For example, in the Gaia filters, they nailed down the GBPG color to 0.324 with an uncertainty of just 0.016 magnitudes, and GGRP to 0.494 plus or minus 0.020 magnitudes.
That sounds incredibly accurate for something derived indirectly.
It is. Getting the sun's fundamental colors pinned down this well in these standard widely used systems is a major recent improvement, and it's thanks almost entirely to having these large, high-quality samples of solar analogs identified by Gaia.
Okay, let's pull this all together then. We've seen how hunting for stars like our sun, it's definitely not just some academic curiosity.
Not at all. It gives us this crucial perspective on our own star's life story, its past and future. It helps us build better cosmic clocks.
It refines the fundamental calibrations that underpin, well, almost all other astronomical measurements.
Right. It sheds light on how our galaxy's chemistry has evolved. It lets us test fundamental physics across cosmic distances.
And amazingly, it even helps us nail down the basic properties of our own sun, like its precise color.
Exactly. And the Gaia mission, as these sources make abundantly clear, is just transforming this field, taking the number of known candidates from dozens to thousands, even hundreds of thousands.
It's opening up a whole new era for this kind of science. So many more stars to study.
Absolutely. And, what's really fascinating to think about is the ripple effect.
How so?
Well, if using these twin stars lets us measure the sun's color so precisely in standard systems, what does that say about the ultimate accuracy of all the other measurements we make that are somehow tied back to the sun as a reference point?
Huh. That's a deep question. It could subtly shift our understanding of many things.
It could. And thinking further ahead, as we find more and more of these solar analogs with Gaia and future missions, what happens if we find one that doesn't just look like the sun, but also has a planet that looks just like Earth orbiting it?
A true Sun-Earth analog system.
Yeah. What could that discovery tell us about how common, or maybe how incredibly rare, our particular setup here in the solar system really is out there in the vastness of the galaxy?